Picking up right where we left off, discussing the vibration of polyatomic molecules. So I know that you've talked about this in CHEM, ad nauseum. But of course, in this class, right, we're going to add a little PChem twist to topics that you've already previously discussed. And so my two favorite molecules, H2O and CO2, I'm going to use these as good examples to discuss the vibration of polyatomic molecules. So first, I want to introduce this concept of normal modes, and I realize I should have had a definition up here, so I'll read you a definition. So a normal mode is an independent, synchronous motion of atoms or a group of atoms that may be excited without leading to the excitation of another normal mode. So in other words, these normal modes, these modes of vibration, as we said, are independent, synchronous motion of atoms or groups of atoms. And each normal mode, the word independent, right, it's independent from the other normal modes. Okay? So these vibrations are all separate energy transitions. Okay? And so there's a couple of equations for the simple polyatomic molecules. 3 n minus 5 normal modes for all linear molecules, and 3 n minus 6 normal modes for all nonlinear molecules, where n is the number of atoms. Okay, so for example, with water, we know water has 3 atoms, so 3 times 3 minus 6 is 3. Okay, so water has 3 normal modes of vibration, and here they are, right, that we affectionately know as the symmetric stretch, that I'll write sim. Okay, and so typically that's given as nu sim for the symmetric. We know there's, and let's demonstrate that, right? So if my oxygen, or my torso is oxygen, and my arms are hydrogens, right? The oxygen kind of moves down just a little bit while the hydrogens come in, okay? And even though this is a symmetric stretch, it does end up creating a dipole moment because we know that water is asymmetrical. So this is observed in IR spectroscopy. And for an isolated gas phase water molecule, a singular molecule in the gas phase, this would occur at 3652 wave number. And so this number right here, that would be the Q branch, okay? In a single gas, right? An isolated gas molecule. Of course, when this vibrates, it'll stimulate the rotations in the gas phase, but this would be the line associated with the Q branch, okay? So, and then of course there is the asymmetric stretch, typically written as VA-sim, or sometimes just nu A-sim. Sometimes it's just written as nu AS. So some kind of qualifier to let you know that's the asymmetric stretch. And my oxygen kind of moves, oops, I'm looking at my reflection. I should just focus on what I'm doing. So an oxygen moves in like this with this hydrogen elongated, and then it alternates, okay? So I like to think of these as like the interpretive chemistry dance moves, right? So this is a nice symmetrical stretch, okay? And it occurs at very similar energy as the symmetrical stretch, 3756 wave number. And then finally, the third and final normal mode of water is the bend, right? Where now these things will bend in and out of a plane. Okay, and consequently, that's a much lower energy stretch. And so what we want to think of, these actual energies or frequencies, they are related to the frequency in which a bond is oscillating. And that is the frequency of light required to stimulate that vibration to go up to an upper level, okay? Where it will oscillate then at an even higher frequency in that upper level. So that 3652 wave number, for example, right, is the energy required to stimulate that vibration to vibrate at a higher frequency relative to its ground state. Okay. So if we look at carbon dioxide, we also know it's got 3 atoms. It's 3 n minus 5 because it's a linear molecule. And so 3 times 3 minus 5 equals 4. So 4 normal modes for carbon dioxide. So we know that there is the asymmetric stretch, right, which is shown right here. Okay. So V asym. Right, and similarly to the water, this is when one bond compresses and the other bond is elongated, and then it recoils, okay? So we've got this nice, lovely asymmetric stretch. Of course, that also means we have the symmetric stretch, right, where it just does this, okay? And as it turns out, oops, I think I labeled these incorrectly. I labeled these incorrectly because that symmetric stretch for CO2, notice it doesn't have an energy associated with it. That's because it's forbidden. So it does not result in a dipole moment. So it's not observed in FTIR. Okay? But as it turns out, this stretch is observed in Raman spectroscopy, which we'll be discussing next. Okay? So here, at 2349 wave number is our asymmetric. Okay. Yeah. And then finally we have the bending mode. Okay. So if we count up these number of modes of motion, we've got 1, 2, 3, 4. Okay. So this asymmetric would occur. I'm sorry, I was talking to my son back there. It would occur at 1388 if it were observed, but it is not observed, so we don't see that. Okay, apologies for that confusion. But at 2349, that's our big prominent CO2 peak that we see not only in FTIR spectra, but what's also principally responsible for the greenhouse effect. Okay. So that's the strongest line for CO2. And then there's 2 bending motions, right, where I can either do this or this, but because CO2 is linear, those are both degenerate. So let's label that new bend, and here, of course, I forgot to say new bend. Okay, and this normal modes, right, that just predicts how many normal modes we have. It doesn't necessarily tell us how many peaks there will be on the IR spectra, because we have to remember our selection rule that there's got to be a dipole moment. All right.